Good evening, everyone, and welcome to the second problem-solving session for the course Computational Continuum Mechanics. I'm Naresh. In case somebody is joining for the first time, I'm Naresh. I'm a researcher at the Department of Civil Engineering at IISc. I work in structural mechanics. So today's session, let me give an overview before we get started. So we'll have a quick recap of the last session, whatever was covered in the last session. And then we started off with the solution of a nonlinear truss problem. We'll finish it today. Then I also realized that the assignment 2 is due on the same day. So by day after tomorrow, both assignment 1 and assignment 2 are due. So I have some problems so that you get a practice before you submit assignment 2. Then we'll also have some small bits of coding to visualize the solutions we derive for this nonlinear truss problem and a few others. And before we get started, if you have any doubts in the last session, you can ask. And if there are none, I'll just proceed with the recap. So this is where we started off motivating the course last time. So we said we have a physical system, which could be anything complicated. And from the physical system to the idealization, we go by assumptions. And these assumptions are based on physical observations. So these take us from the physical system to an idealized thing. So we looked at the truss problem. So where the physical system has gusset plates and multiple three-dimensional bodies. And we get to this idealization of boundary conditions and the loading and some idealization of the member behavior. From idealization to the governing equations, which are typically partial differential equations, we get by applying mechanics principles, which are mainly equilibrium, stress-strain relations, and the strain displacement relations. And from the partial differential equations, which usually govern the physical problems, we get, so these are the mathematical models. So these are the PDEs are mathematical models. For example, you will already be familiar with the heat conduction governing equation, which is just Laplacian, the temperature field is equal to, can say, some heat conduction plus some boundary conditions. So this is a mathematical model. And in general, this cannot be solved in closed form. So we often resort to numerical methods. So from this is a continuous system. From this, we get to a discrete system, which is usually something like AX equal to B, a system of linear, simultaneous linear equations, a linear system of simultaneous equations. This is achieved by any of the numerical methods, such as the finite element method, the finite difference, and the finite volume method. There are also certain advanced methods that help us go from the mathematical model to a discrete representation of the mathematical model. Once we have AX equal to B, the next step is just solution, where we solve, if A is invertible, you get it as X equal to A inverse into B. And this is the last step. This is just by a linear solver, linear or nonlinear solver. So for nonlinear systems, we get a nonlinear solver. And for linear systems, we just have to invert a system of equations. So this is just, we need a solver to go from discretized system of equations to the actual solution. We also looked at the continuum assumption, where we said real materials are made up of atoms, and every atom faces forces from all other surrounding atoms. However, when you consider a material point in continuum, you make this assumption that at a scale much higher than the scale of the atoms, you can treat all the fields, such as the displacement field, temperature field, stress field, and the strain fields, as continuous functions. In reality, you can only define it as particle is present, but you can extend the definition to continuous functions like this at a scale which is much higher than the scale of atoms. We also looked at what linear systems are. So linear systems are, you can consider them as a black box, where if you give an input X, they return an input Y, which is Y is equal to f of X. And if the system is linear, it has to obey this superposition principle. So if you feed in X, it returns f of X, which is Y. If you feed in alpha x plus beta alpha x1 plus beta x2, which is a linear combination of inputs x1 and x2, it has to return the linear combination of the corresponding outputs f of x1 and f of x2. Here x1 and x2 are arbitrary inputs, and alpha and beta are some arbitrary scalars. In mechanics, as you see, there are various various levels of relationships. So one is equilibrium. The forces, sum of all forces at a point has to be zero. The sum of all moments have to be zero. Then we have the stress-strain relations. Then we have strain displacement relations, and we have boundary conditions. For a problem to be linear, for a structure or solid to be linear, we want all of these relations to be linear. So here, let me take the example of a cantilevered beam. If you just look at the case of a cantilever beam, it is rigidly supported at the left end, and you apply either a load or a displacement at the right end. So the beam takes a curved shape like this, and it has a tip deflection of p. Now, if you start systematically, you look at equilibrium. Are the equilibrium equations linear? So you take a section at a distance x from this support. That section will expose a moment of m. And I have already made an assumption by drawing this member straight. But actually, you will have a member like this. The original member will be somewhere here, and the moment will act here. And we know in linear structural analysis, this moment m is given by the distance at which it acts multiplied by the force with a minus sign, assuming with this convention. So P is equal to minus x minus px. M is equal to minus px is what is the relation, is the equilibrium relationship. And if you don't consider the deformation of the beam, it is linear. However, if you consider the load to act on the deformed structure, which is the actual reality, load doesn't act on the undeformed structure. As you increase the load, the structure deforms. So when it is in equilibrium, it is actually the forces in the deformed configuration that are in equilibrium. So here you have ignored geometric nonlinearity. When you consider the loads to act on the deformed structure, it is called it is nonlinear. You don't really know. So the actual distance x is along the center line of the beam, but the deformed center line is something like this. This distance is something you can call it as some x2, and x2 is actually a part of the solution. We don't know x2. So if you consider the deformation, it is a geometrically nonlinear problem. Right? So that gives rise to the first nonlinearity, which is geometric nonlinearity. The second thing is, in a given section, from beam theory, the stresses are linearly distributed. So actually the strains are linearly distributed, and the stress and the strains are related as sigma is equal to E times epsilon. However, say when you have plasticity, if it is yielding, the stress cannot increase beyond the yield stress. So stress is always less than or equal to the yield stress. So once the beam starts yielding, you will have a distribution like this. So the stress will be capped at a value sigma y. And in other cases, you will have sigma less than or equal to sigma. So whenever you have a constant, when you have plasticity, the stress can never exceed the constant value sigma y. But this is a nonlinearity. How do you express the stress strain behavior? So here, as you increase the strain up to a certain point, the stress increases proportionally. And beyond that point, assuming there is no hardening, you have a yield stress. So this is a nonlinear. This is it's consisting of two linear segments, but in general, this is nonlinear. So in this region, you have the elastic modulus as E, and here the elastic modulus is actually 0. The stress at constant stress, you can have indefinite straining. Therefore, if you express in a general form as sigma as a function of the strain as some tangent modulus, which is a function, which itself is a function of the strain multiplied by the strain, this in this case is E when corresponding to this, you can have a yield strain. E when strain is less than the yield strain, and 0 when strain is greater than or equal to yield strain. Therefore, this is a nonlinear material model. The nonlinearity is absorbed into D. So this takes care of material nonlinearity. Then we have something called kinematic nonlinearity, which is what appears at boundaries. For example, you take a block, you take a rectangular block, and press it against an elastic substrate. Right? You can treat this block as a rigid body, and you can apply a force P onto it, and this can be some elastic substrate. So typically, such problems are seen in foundation engineering. You have a foundation which is resting on soil, right? In such problems, you know where the so for the soil, you know where the load is acting. So the load is acting over this region. But we know that the total load is P, but we don't know the distribution of the load. So this soil can be assumed as an elastic medium. It deforms in a certain manner, and over this region you have some unknown distribution of pressures. And this distribution of pressures has to be solved using some method. Now here we know the region, the location of, we know where the load is acting, but we don't know the value of the load at these points. So this is one kind of boundary nonlinearity. So this is the soil or the elastic medium. Right, it doesn't have to be soil. You just take anything, you can just take anything and press some conforming block onto it. We know the elastic medium, but we don't know the magnitude of the pressure. What is this? We don't know this. So such problems where and this is the boundary of soil, right? This is a boundary condition on the soil. So we know from minus infinity, say this is minus A, this is plus A. This you can call it as x equal to 0, which is the y-axis, and this is plus infinity. So we know that from minus infinity to x is equal to minus A, we don't have any loading. From minus A to plus A, we have some loading, and from plus A to infinity, we don't have any loading. So here it's a displacement type boundary condition, and the pressures are unknown. So this can be taken as a this is the displacement is unknown. We know the total force, and this is one kind of kinematic nonlinearity where the boundary conditions depend on the displacements, and the displacement themselves are a part of the solution. So the location on the boundary is known in this case, whereas the values are unknown. On the other hand, take the same soil or a substrate and you press it against a spherical ball. So in this case, say the ball has a constant radius r, and you're pressing it with a force P. And so this is typically an indentation problem encountered. So this is a foundation engineering problem. And this is an indentation problem which is encountered in material testing and mechanical applications. So you take a rigid ball, rigid indenter, and press it against some metal substrate. So in this case, initially, the point of contact is just 1 point. But as you press it, the point of contact just grows. So it will take some configuration like this. So this is the ball. But here, we don't even know which region is going to be in contact. So this region A is actually unknown. So we don't know what A is. And over this region, we also don't know the distribution of pressure. So here we know the region A because we know the size of the block. And it will deform like this. There is no contact between the sides of the block and this soil. But here, since this surface and this surface are not conformal, the contact will be initially at a point and slowly it will grow. With increasing P, this will grow further. So here the condition is we really don't know over which region the contact is happening. And over that region, we don't know the distribution of the contact pressures. So this is a geometrically nonlinear, kinematically nonlinear problem where the boundary conditions, location is also unknown and the values are also unknown. The other kind of nonlinearity is force nonlinearity. Suppose you have you have a cantilever beam, and the force is acting such that it is always perpendicular to the beam. This boundary condition is typically, it's hard to get it in reality, but you think of it as some kind of pressure. So pressure acts always normal to the uh, surface. A pressure acts always normal to a surface. So which means after the beam bends, this force is still normal to it. So such a force is called a follower force. So we have to solve this problem in the deformed configuration because the force is acting at some angle with the vertical, right? It acts at some angle with the vertical. But that angle itself is a feature of the solution of the problem. So here, the boundary condition, the force boundary condition depends on the solution. So this is a kinematic nonlinearity, force nonlinearity. And we also have this we didn't look at, so we only looked at geometric last time. These I'm just explaining right now. And we can classify the nonlinearities based on their severity as mild and rough nonlinearities. So when the nonlinearity can be smoothly represented, say you have a smooth nonlinearity such as you just have a nonlinearly elastic material like this, and at every point you can get the Young's modulus as a function of the strain. You just have sigma is equal to uh, or the rate of sigma dot is equal to E of epsilon times epsilon naught. At any point, if you draw a small tangent, you can get the slope of the tangent as a function of the strain level at that point. So this is a nonlinear elastic material, and this is relatively easier to handle. Right? This you just have to integrate. This is easier to handle. However, if you have conditions like plasticity, where you have an equality or an inequality constraint. So plasticity, you have an inequality constraint, which is sigma is less than or equal to sigma y always. And you have contact problems where you have this condition. For example, here, you can say that the gap between this surface and this surface, call it as some delta. This delta, which is a function of x, should always be greater than or equal to 0. If this gap is less than 0, it means this solid has gone into the other solid, which is unphysical. So in contacts, you have inequalities such as the gap is greater than or equal to 0. So whenever you involve inequalities and equality constraints, so when you have inequality or equality constraints, you can have sudden changes in the solution. As you look at the some characteristic of the solution, you can have sudden changes. For example, in plasticity, you have something like this. There's a sharp change in the solution. And in contact also, you can have similar cases. So these are called rough nonlinearities because the response is quite discontinuous. On the other hand, mild nonlinearities are very smooth. The response is quite smooth. So here we have these two examples from Sir's lectures. So, so you look at a cantilevered beam. This is a rigid bar, and at one end you have a torsional spring, and at the other end you are applying a certain force. Suppose we are interested in deriving the relationship between this force and this rotation. We establish equilibrium in the deformed configuration. So this is the free body diagram. You apply a force here. There will be an equal and opposite force at this support, and it is allowed to rotate but not freely. There is a spring which resists the rotation as m equal to k theta, and this k can be treated as constant. Therefore, this is a linear spring. So here the material is linear. Material is linear because k is a constant. Let us analyze this. So here you have, this is the original length, and this length is L. This angle is theta. You have a force F here. You have a moment acting M here, and you have an downward force F here. So this has to be in equilibrium. These two forces are acting at a distance of F, L, cos theta. That should be equal to the moment. So this is the you take moments about this point. the external force is this, the internal moment is this. But what is the internal moment? The moment is also equal to k times theta. Therefore, F is equal to k by L theta by cos theta. So the relationship of F on theta is nonlinear. Why is it nonlinear? If it is just proportional to theta, it is linear. So if you have to answer why something is nonlinear, just take theta as 2 theta. If F becomes 2F, then it is linear, right? So this is a necessary condition. This is not sufficient to say it is linear. If this does not happen, then it means there is some form of nonlinearity. Okay. So here, what is the kind of nonlinearity? F is equal to k by L theta by cos theta. But if you don't consider the deformation, if you don't consider the deformed configuration, and you just establish the equilibrium, assume that theta is very, very small, right? That is the usual assumptions of linear structural analysis, linear elasticity. If you assume there is a spring of k, a constant k, you are applying a force F, and you assume the deflections and the rotation are very small, you will get m is equal to Fl. But what is m? M is equal to k theta. K theta is equal to Fl, which means F is equal to k by L theta. So this is the linearized, or yeah, this is the linearized relationship. Whereas this is the correct geometrically nonlinear relationship. Are these two related? Because if theta is small, this has to reduce to this case, right? Sorry. Yeah, if theta is small, we want this to reduce to this case, right? So let us check that. So you can write this F is equal to k by L theta by cos theta as k by L theta divided by cos theta. You can expand it in the form of Taylor series. You get it as 1 minus theta square by 2 factorial plus higher order terms. Now you can write it as k by L theta into 1 minus theta square by 2 factorial plus higher order terms, the whole raised to minus 1. Call this entire quantity as epsilon, which is of the order theta square. Now you can write it as k by L theta. So 1 minus something inverse is just 1 plus epsilon square plus and so on. But here epsilon itself is the order of theta square. If you neglect all the higher order terms, you are ending up with k by L theta. Therefore, if you start with a nonlinear equation, you can always linearize it and get the corresponding linear equations, right? The other example is buckling. So this is again a rigid column. It is supported by a torsional spring at the lower end, and you're applying a force P. Initially, this one remains straight, but as you increase the load, at a certain load, it is capable of generating a lateral deflection, right? It can start rotating. So yeah. So the structure initially is like this with a torsional spring of constant K. You're applying forces F here. Now, if you establish equilibrium in the undeformed configuration, it is just you have a structure like this. You're having equal and opposite forces, no eccentricity. So F is actually undetermined. F does not depend on, for any F, this is not going to have any rotation, right? F does not depend on theta. Or rather, F does not depend on K or anything, right? In general, if you have, this is what is governed, this is what is given by the linear analysis. However, that is not true. That is just one solution, right? This column can remain straight. That is one solution. You make a slight perturbation. Make a slight perturbation theta. Assuming theta is much small. Theta is very small. Assuming theta is very small. You can ignore the effect of the reduction of height, right? You can ignore that height. So In that case, what do you get? The moment at this support is equal to FL. If theta is very small, you can approximate. So this you can approximate. So FL sine theta, right? This M is actually FL sine theta. This is L. This is a rigid link L. It's FL sine theta. But if theta is very small, you can take it as FL theta. But what is M? M is K theta. So K theta is equal to FL theta. What are the solutions? This gives rise to two solutions. One case theta is equal to 0, and the other solution is F is equal to K by L. So what does this predict? This predicts that either this column remains straight with theta equal to 0, or the force reaches a value K by L with theta undetermined. So theta is statically indeterminate when force reaches a value K by L. So if you plot the response, it is like uh, up to a certain value of F, you can call this F critical, right? You can call this F critical. Up to that point, as long as F is less than that value, theta remains 0. But once F column remaining straight, but that is unlikely because it is in unstable equilibrium beyond a point. So the other equilibrium solution predicted by the linear analysis is F takes a value K by L and theta can be anything. But in reality, that doesn't happen, right? In reality, because you have a spring K, you have a spring here. So as F moves away, the spring will start generating more and more number of forces. So this is the prediction of geometrically linear analysis. Geometrically linearized buckling analysis. Now, if you look at the actual geometrically linear nonlinear problem, the moment is still we just derived, it is FL sine theta. But what about M? M is K theta. You cannot put theta is approximately equal to sine theta. So you get K theta is equal to FL sine theta. Therefore, the force as a function of the rotation is uh, K by L theta by sine theta. Now, when can I write this? Have I made any assumption while writing this? From going from this equation to this equation, have I assumed something? Yeah, you can guess. Have I made any assumption while going from this to this? Here there is no. Here it's all clear. I'm just substituting things here. What did I do here? I've divided on both sides by sine theta. But when is it allowed? It is allowed when sine theta is not equal to 0, which means theta is not equal to 0. So one solution to this equation, this can be satisfied either with theta equal to 0 or with this condition. So again, we have two solutions. If you plot force as a function of the lateral deflection, you can either have the column straight, or you have another solution. But that other solution is, unlike this case, it is not indeterminate. So when you do a geometrically nonlinear analysis, there is a theta corresponding to every value of force. Now let us visualize these. For what it is, we'll visualize this. Right here you have one equation. Here you have something. Let us visualize this live. Okay. So you can open. You can also do it alongside. Okay. Any doubts before we get to that point? If you have any doubts, you can ask. Okay. Seems like there are no doubts. Uh, let us visualize this solution. Okay. So you can open this Google Colab. Like Google Colab notebook. Just search for it. You can open this, and this opens. If you're logged into Google, it opens a live coding environment. You can just use this to visualize these functions, right? So okay, before we even plot anything, if you just have in this case, right? If you have f is equal to k by L theta, f is proportional to theta. When theta is equal to 0, f is 0. And when theta is equal to something, f is equal to k by L theta. So you have a line like this when you have linearized thing with the slope k by L. Now, when you have theta by cos theta, if you have to guess the shape, k by L theta is something like this. Cos theta in the first quadrant decreases with increasing theta. Therefore, when you have 1 by cos theta, it actually increases with uh, increasing theta. So this k by L theta is actually magnified by another factor 1 by cos theta. Therefore, initially it may start like this, but quickly go faster than, it will rise faster than the linear relationship. So this is what you would expect. And for this problem, what do you expect? So linear, here it's all clear. So f critical is a constant when theta is not equal to 0. But when you do a nonlinear analysis, you get something like this. Again, k by L theta, k by L theta is linear, but sine theta is also increasing in the first quadrant. So this is somewhat difficult to guess. But you know that theta, you have this relationship. Theta is greater than sine theta, greater than or equal to sine theta, which is less than or equal to tan theta. You know this relationship. So this value, theta by sine theta, is going to increase faster than theta. So here you will expect at a value at theta equal to 0, you can have k by L. From there, you have the other solution, which is taking off like this, right? So we can visualize that as we have this. So you can use this library of Python. You can import sympy, right? And then for the cantilever problem, you can create symbols. What is wrong? Mm, yeah. So for the cantilever problem, we can define a symbol. So you just to visualize here, we can just take k and L as 1. Okay. So just make k equal to L equal to 1. You just want the shape, right? K equal to L equal to 1. And create a symbol for theta, right? So from this library, you can use theta. And what is the relationship between f and theta? F is equal to k by L times theta by cos theta. So again, cos has to be imported from this sp dot cos theta, right? So this, okay, sorry. So you can import, you can use this to plot the function f as a function of theta. So use sp plot. The y-axis is f, and in the x-axis you want to plot t. In which range you want to plot it from 0 to say when the rod becomes so when theta equal to 0, sorry, where is it? So when theta is equal to 0, the rod is horizontal, and when theta is equal to pi by 2, the rod is vertical. But if you substitute theta equal to pi by 2 here, the denominator cos pi by 2 becomes, it blows up, right? So let us stop it somewhere before it, say at 90% of pi by 2. Okay, so say this is 0.9 times 90 degree, which is about 81 degrees. So at 81 degrees, it is just 0.9 times pi by 2. Okay, so you can plot this. Let us just run everything. Right, this, 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 and this. So this is how it looks. So initially, you see the response is kind of linear. Here it is somewhat linear. But as theta increases, the force starts shooting out. Okay. So this is why graphically you can see linear elasticity is a good approximation. When you are initially close to the unloaded case, uh, you have the response predicted by F. F is equal to K by L theta. It is a kind of proportional. Later it starts becoming curved. Now use the same thing for the buckling problem. Use the same theta. So theta is fine. We can plot for the buckling problem. Let us call the load P. P is equal to what did we get? K by L. And what was the? It was theta by sine theta, right? So it was T by SP dot sine theta. And this let us plot from. So P can be plotted from theta going from 0 to. So here there's a problem the left hand side. So you're dividing it by sine theta. So if you substitute theta equal to 0, you will have an issue because denominator will get a 0. So let us start from a small value close to 0. Say 0.0001. From there up to, I can plot it right up to pi by 2 because it's not going to vanish. So plot it up to 2. Okay. So let us plot this. Yeah. So this x-axis is at a weird position, but you can see it starts at 1. 1 is what? It's just k by L. K by L, we took that as 1, k equal to 1, L equal to 1. So it starts horizontally. And that is what is predicted by the linear theory, right? Yeah. So linearized buckling analysis predicts that close to this point, when theta is very small, you have this force deformation curve is horizontal. So that is what is also predicted by the nonlinear theory. So here it starts horizontally, whereas here it starts with the slope of 1. So here it starts horizontally and it becomes nonlinear. Okay, any doubts at this stage? Were you able to follow? Did you try? Could you try doing it live? It's easy. Right? It's if you have any doubts, you can ask again. I'll wait for a minute. And not a minute, maybe a few seconds. It's okay, right?
Yes, sir.
Yeah. Okay, now let us go to this little bit more involved problem. So here, this is what we started off last time. Yeah. So here you have a nonlinear truss member. It's my drawing too. So here we have a nonlinear truss member. Initially it is in this configuration with length capital L, area capital A, and volume capital B. And you're pulling it up with a force F, and it extends to a length small l. Its area decreases because when you're pulling it, the area will decrease, become small a, and the volume also could change depending on how it is. So initially the height is capital X, and as you pull it up, the height becomes small x. So let us solve this problem. Last time we started off with listing the unknowns. So what are the unknowns in this problem? Right now, small x is unknown. The force F can be treated as known, right? We are applying a force and we want to find x. This theta is unknown. The length L is unknown. This area, volume are also unknown, right? And what are the knowns of the problem? Suppose the initial angle is theta naught, right? Let us call the initial angle theta naught. The knowns of the problem are theta naught is known, capital L is known, A is known, B is known, capital V is known. Now let us assume that the strains are small. Strains are small and rotations and displacements can be big. The reason I'm doing this is I don't want to deal with material nonlinearity. So if the strains are big, right? So I said we have the strain displacement relation, stress strain relation, and the equilibrium, right? The relationship between the forces. So if you have large strains, you cannot use strain as delta L by L, because delta L by L means it is proportional to it linearly depends on the displacement. So it is no longer valid. When you have big displacements, you cannot use this anymore. But let us assume that the strains are small, but the rotations are large. And this relationship, sigma is still equal to E times epsilon. Let us assume this. So if the strains are small, then at any point, the cross-sectional deformation will not be much. So you have A is equal to, A remains A, and B will be what? B will be A times L. So it is nothing but A times uh, small v by mm, capital V. So here, sorry. Yeah, so once you assume the strains are small, this is also known, this is also known. So you can strike off these two from the list of unknowns. So we only have x, theta, and L as unknowns. Now, let us, instead of dealing with x, let us use this displacement as delta, right? So small x is equal to capital X plus delta. This is one equation. Uh, and other unknowns are, we don't know the stress in the member. We don't know the strain in the member. And we don't know the force in the member, right? Let us solve all these. So the stress in the member is E times strain in the member. The force in the member is the initial, it's actually the final area, but we have assumed that the area doesn't change much. So A times the stress in the member. So it is nothing but E A epsilon. Now what is left? We want a relationship between epsilon and delta. So to do this, let us use the precise geometric details, right? So here, what is L square? Small L square is equal to is equal to this D square plus X plus delta, which is small x, the whole square. Now, what does this give? This gives a relationship between L and delta. So let us have this as one equation. What is the other equation? The horizontal displacement, this D, remains unchanged. So capital L square is equal to D square plus X square. Okay. So let us solve this. Nonlinear. So let us solve this. I will need the and let us define this as the change in length by original length. So we should actually take the current length, but assuming the strains are all small, you can take this as the original length. So which is nothing but L minus L by L. So it is L by L minus 1. So this you can take it as one equation. What is L? We just defined it. L square is equal to x plus delta the whole square plus d square, which means the strain is just which means L is square root of x plus delta the whole square plus d square. Strain is L by capital L minus 1. So it is square root of x plus delta by L the whole square plus d by L the whole square minus 1. Now simplify this further. We can write this as x square by L square plus 2 delta x by L plus delta square by L square plus delta square by L square plus d square by L square, then whole thing minus 1. What is this? Let us club these two. Right? What is the sum of, sorry, not these two, these two. Okay. So if you add the first term and last term, what do you get? You get x square plus d square by L square. What is that equal to? Looking at this figure, x is this, d is this, L is this. So what is it equal to? X square plus d square by L square?
1, sir.
1. Yeah, right. Perfect. It is, so numerator is L square, denominator is L square, so it is 1. So the strain is equal to square root of 1 plus 2 delta x by L square plus delta square by L square minus 1. So we have found out the strain. So let us also strike off strain from our list of unknowns. We found L also, so let's strike out L from the list of unknowns. Sorry, we didn't find L. Find L. Did we find L? Yeah, we found L. Yeah, L can also be striked off. So from strain, getting stress is nothing. So get the stress. What is the stress? Stress is nothing but E times strain. So here it is E times this whatever is there here. Okay, let's put it in. Now, okay. So let's summarize. L is equal to this square root of x square x plus delta whole square plus d square, right? And strain is the strain is fine. Strain we just got. The stress is E times the strain, and the force in the member is A times sigma. So what is yeah, so we can also strike out the force. We can also strike out the stress, right? Only unknown is theta right now, but let's come to it. So the force in the member is A times sigma, but sigma is E times the strain, and the strain is L by L minus 1. In place of L, you substitute this. Okay, so force is also known. So we have used the strain displacement relation. We have used the stress strain relation. What is remaining? Equilibrium, right? So at this point B, let us draw the force diagram. You have a force applied upwards, F, and you have a force, Fs, which is acting at an unknown angle of theta. Because as it undergoes large rotations, this theta will not be equal to the initial theta naught. But let us just have theta. What the relationship between F and Fs is Fs sine theta is equal to capital F. What is sine theta from this diagram? From this diagram, sine theta is opposite by hypotenuse, which is x by L. So F is equal to Fs x by L. What is x? X is x plus delta, and L is just L. L we know. L we know in terms of delta. Fs we know in terms of delta, and delta, yeah. So right now we have the force in the member. The force that should be applied as a function of delta is AE L by L minus 1 multiplied. So this is Fs, right? This is Fs multiplied by sine theta, which is capital X plus delta by L. So this is nothing but AE capital X plus delta. You can multiply this L here, so you get what do you get? You can take this capital L outside. So L minus L by L minus 1. So it is like 1 minus 1 by L. And L is in terms of delta. So you can just substitute that finally. So the final expression is the force is equal to what do we have here? AE x plus delta into 1 minus 1 by square root of so L we have something like this, right? So it is x plus delta the whole square plus d square. Okay, so we have solved the problem. So we got F as a function of delta. So corresponding to any delta, we can see what should be the force that is applied. But how do we really don't know the values, right? So we should see how this curve looks. This is a highly nonlinear curve. So let us try to plot it in Python as we just did. Okay, so let us consider a shallow truss. Take a shallow truss because it has some interesting properties. Let us take, right, let us take this height, initial capital X as 0.05 meters and this length as 10 meters. Okay. So that is that, and AE and all you can take it as 1. Take AE as 1. Take capital X as 0.05. D as 10. Okay. Now let us plot this expression in the same file. So again, now let me call a symbol delta D as P dot symbols delta. Okay. What is our small l? Small l is this thing, x plus delta. So it is like square root of sp dot sqrt of x plus delta the whole square. So x plus delta. So in Python, the power is double star 2 plus d double star 2. So before that, I didn't define what x and delta are. So x is 0.05 and capital D is 10 meters. Right. So we defined L. And what is F finally? So AE you can take it as 1. AE you can take it as 1. So F is finally AE multiplied by x plus delta multiplied by 1 minus 1 by L. Right? So let it evaluate all this. Okay, it has evaluated. Now let us plot this. So let us plot F as a function of delta in the range. So I can, so this is a truss like this. So you start with so that's okay. Let's do one thing. So here you have assumed forces upward as positive, right? You have taken forces upward as positive and delta upward as positive. We can proceed with it, but let us take the other case of delta negative and force also negative. So if you take a tennis ball, you cut a tennis ball, not at the equator, you cut it along one edges, and then you apply a small force. At some point, it will just snap to the other side, right? So let us see if we can simulate something like that using this simple truss, right? So you just have one member like this. You're applying a force. Now let us just reverse the force, right? So wherever you have force F, you put a minus sign. And in place of D also, you can put a small minus D, right? You put reverse the positive signs of force and displacements. So here also you have a minus D. You can also proceed with the other way, but you have to plot in the negative direction. So let's say D goes from 0 to, so the total height is, this is like 0.05 meters. Let us take it to the case where the truss member goes to the other side. It passes through this and then it goes to the other side and goes to. So let us plot this up to say 1.25 meters. Okay, delta is going from 0 to 1.25 meters. Let us plot this. Okay, so something is not correct. So x is fine. This is fine. D is fine. D square x. X plus delta, the whole square, x minus delta. Let us say x minus d whole square plus
So the equation of F divided by L term is also there, no sir?
right, that's the problem. Yeah, thank you. Yeah, that's a good catch. Yeah, so here it is sine theta. So here you have an L. That's it, that I missed. Perfect. Yeah, very good. That's a good catch. Yeah, so I just have to divide it by L. No, I think that has been taken care, right? So let's look at the dimensions. AE x by L. Yeah, something is off with the dimensions. You have to look at it carefully. So here, this is fine. This epsilon is fine. This part is fine. This is okay. Okay, this is gone. X plus delta by L. Yeah, here there's an L that is missing, right? So here you have this L. Yeah, it's a capital L here. So capital L is x square plus d square. Let me do that. So this is divided by capital L. So we write capital L is equal to this is divided by L. And here there is an L. So this is dimensionless. AE by L F. Yeah, now this will be right. Got this. Fine. So let me compare with the expression that I have. You have x plus delta, that is okay. Um, you know why this problem happens in part one. So delta is AE x plus delta by small l into one previous step. Let me write it afresh. That's it. So the expression we had was f is equal to uh, AE multiplied by the strain and the multiplied by x by L. This is sine theta. So this is, and the strain was L by capital L minus 1 multiplied by x by L, which is AE. Let's not simplify this any further, right? So let it be L by L minus 1. And this is x plus delta by small l. Yeah, let's just write, because anyway we are computing L, we can just substitute in the code as it is. So we have L, we have capital L, we have F is, and in place of delta, I'm putting minus delta just to look at the compressive forces. AE is 1. So F is minus AE, x plus delta by L. So here you have a small l. And here we have L by capital L minus 1. Right? So here we have L by capital L minus 1. Let us evaluate this. Let's evaluate it. Well, let's plot this. Okay, so let me take it to a smaller extent. So let me just plot it up to 1. Right. So let's take smaller and smaller values, say 0.05. Yeah. So let me plot it up to a value of 0.1. Okay, I shouldn't have plotted up to 1, right? So it's a plotting issue. The expressions were right. There was no issue with this. So this height is initially 0.05. So I should have only plotted up to 0.05 in the negative direction. So let me plot it up to 0.125. Yeah. So what we see is initially as we increase the force, uh, that point B starts moving downwards, right? At some point, we cannot apply any more force without causing an instability. So there is a critical load here. So at this point, the maximum force that can be reached is achieved. Then suddenly, to keep it in equilibrium, you have to reduce the force beyond that point. If you don't reduce the force beyond that point, if you just keep loading it with increasing force, that the truss will accelerate and it will go. So I can copy this, put it in the slides. Yeah. So what this physically signifies is, so at this point, you have the truss like this. It starts deforming in the direction of application of force up to this point. Beyond this point, you cannot increase the force any further because for the truss to be in equilibrium, you have to decrease the force. So with any further deflection, the force has to decrease. So what it means is if you apply any more force, the truss will just accelerate. So it will just jump from this point to this point, and further it will start increasing the load in there. So this process is called a snap through. And by this, when it crosses this, it has already crossed the maximum. So from here to here, it will just snap. So from this point to the other end, right? So this is where we started at 0.05. And when it's at 0.1, it's already at the other end, right? So with zero force, it will reach, if you just touch it and leave it at this point, right? Take it to the critical point and you just touch it and leave it, it will just snap to the other with zero force. With no force, it will just go to the other configuration. And with further loading, it will just continue in the direction of loading. So this phenomenon is called snap through, and it's a simple demonstration with our truss example. And this is a geometrically nonlinear phenomenon. Okay, so this is okay. And now again, you can get the linear limit. So initially, if you draw a tangent here and take its a slope, that will give you the initial linear elastic stiffness, and you can take it as an exercise. So this expression, you can get the linear elastic stiffness. So in that case, L by L, yeah, you can do that, right? So theta is approximately equal to theta naught. Make this approximation here. So this will become just theta naught, sine theta naught. And this is just a small strain. This will reduce to the small strain expression that you can solve it. And you can get the initial stiffness as AE by L. I think probably it should be sine, yeah, sine theta naught, right? Sine theta naught. Yeah, you can find this. You can figure out whatever this is. So any doubts here? So from this point, we'll get to the week 2 section, tensor algebra and some problems using the tensors. So at this point, if you have any doubts, you can ask. I just got a little confused in the plotting because it was plotting over a big range. That particular snap through phenomenon was not visible when I plotted to 1. Right? It was very small. There are no doubts, then I'll proceed with the vector and tensor algebra part. So assuming that you would have had the chance to look at the lectures. So assuming that you have the chance to look at these lectures, you know what a vector is. So vector, you can think of it as a directed line segment, but the way people define a vector depends on the domain. So in computer computer science and in coding, vector is just an array of numbers, and in physics, people define it as a director line segment, not really a director line segment. So in school days, you would have learned of it as something that has uh, a magnitude and a direction. And in mathematics, hardcore mathematics, a vector is just a member of a vector space, a special set called vector space. It has certain nice properties, but we are not taking that approach. Sir has not taken that approach in this course, but we can also do continuum mechanics with that. And in physics, what people consider a vector is a director line segment whose components transform according to certain rules. According to certain rules with coordinate transformations. So if you just look at the conventional, so we know that particles velocity vector is a vector. So if it's a particle and it has velocity v, this is called a direct notation. Direct notation is you represent velocity v as a vector. You're not interested in its components. So this is a physical quantity of this particle. It has velocity in this direction with some magnitude. But you cannot do operations with this abstract form of v. So vector, you can think of it as a director line segment. This is a direct notation. But to describe this, you need some coordinate axis. So you set up a coordinate axis like this. X1, X2. And the component of v along this, you call it v1. And the component of v along this x2 axis, you call it as v2. So, and the basis vectors. So you can define vectors oriented along these coordinate axes, which are called the basis vectors, which are e1 and e2. So this vector v is v1, the component along the basis vector e1 times the vector e1 plus the component along the basis vector e2 plus multiplied by vector e2. And in 3 dimensions, you will have another v3, e3. So this, the left-hand side is called the direct notation of a vector. The right-hand side is the indicial notation. It's not really indicial notation. You have the components, right? The right-hand side, you can also express it as v1, v2, v3. An ordered pair of 3 components with respect to a specified basis e1, e2, e3. Now we can also rotate this basis to have something else, e1 dash and e2 dash. But with respect to this basis vector, the components will obviously change. So the vector is the same, but its components in the rotated basis can be different. v1 prime, e1 plus v2 prime, e2 prime plus v3 prime, v3 prime. Now, that simple cases, in one case, you can consider the basis vectors like this. In the other case, you can consider the basis vectors rotated this way. And you consider a vector v like this. So let me write this red one as e1, e2, and the rotated one as e1, e2 prime. So in the red coordinate system, the vector v is always the same. It is v1, e1 plus v2, e2. But the same vector, when you express it in a rotated coordinate system, it is v1 prime, e1 prime plus v2 prime, e2 prime. But e1 prime is collinear with v1, which means its projection along its component along e2 is 0. So v2 prime is 0. So it is nothing but v1 prime, v2 prime. And v1 prime is just the magnitude of v in this case, right? So all this is basics, this you know. Now, this summation, right? This is a summation of several components. You can write it as summation Bj, Ej. where Ej are the basis vectors, Vj are the components. And this summation goes from j equal to 1 to 3. But later, in the early part of 20th century, Einstein came up with a summation which is more, with a convention that is more concise. Instead of expressing the summation, the limits, this thing, Einstein just writes it as Vj, Ej, with the understanding that the summation is over the repeated index j. Such an index is called a dummy index, right? It's called a dummy index. Yeah. So Einstein came up with this summation convention. This is called a summation convention, summation or indicial summation convention or indicial notation. So these are the basics. So vector is an abstract quantity. It just has, you can look at it as a directed line segment. Once you choose a coordinate axis, you can express the vector in terms of its components along the coordinate axis, and that takes this summation form. But you can write it as this summation, which is the usual mathematical notation. Or you can also use Einstein's summation convention and drop the summation sign altogether. So in three-dimensional space, this j goes from 1 to 3. So a vector in indicial notation can be denoted just as Vj. Now, the number of, so this is a vector. Similarly, a tensor, say stress tensor, you have two indices, right? Sigma ij. So one index is the direction in which you have the normal to the plane, and the other index is the direction of the component which you're looking at. So these have two indices, and these are in general tensors, although we'll define a tensor shortly. So all are tensors. So in general, vectors, tensors, scalars, all are tensor quantities. So this is a rank 2 tensor. So the number of indices denotes the rank of the tensor or the order of the tensor. And the conventional vectors are rank 1 tensors. What about a scalar field, say the temperature at a point? So regardless of how you orient the coordinate system, the temperature has no direction. Therefore, the temperature is invariant with respect to coordinate transformations. So something like the temperature field doesn't have any indices. So that is a rank 0 tensor or a scalar. So these are all basics. So we have looked at direct notation is just this. Indicial notation is just put the component Vi. And summation convention, as I said, if we have Vj, Ej, you have an index that is repeated. It means that there is a summation over that index going from 1 to some understood number. In 2D it is 2, in 3D it is 3. Let's look more details into the summation convention. Suppose you have a system of linear equation a11x1 plus a22x2 and so on up to an1 xn. Sorry, what have I done? a12x2 plus a1n xn is equal to b1. And so this is like n variables, so you need n such equations. So a21x1 plus a22x2 and so on up to a2n xn is equal to b2. Let it go on up to an1 x1 plus an2 x2 and so on up to ann xn is equal to bn. So this, you can write it as this matrix form. Matrix A multiplying a vector x is equal to. So this is a column vector, not this vector, not a directed line segment. So this is n cross 1, this is n cross 1, and this is n cross n. Now, if you just look at one of these equations, you can write it in a summation form, right? You can write this as, in general, not in summation form, you can write it as ai1x1 plus ai2x2 and so on up to ain xn is equal to bi. And this holds for every I going from 1 to n. So there are n such equations. Instead of writing all the n, I have condensed it to just one equation by using the symbol I, by using the index I. But I can also make it even more concise. I can also use this summation. I can put a summation over j going from 1 to n. Aij xj is equal to bi. Now let us drop the summation as per Einstein's convention. We get aij xj is equal to bi. So here j, if you see, it is repeated and it's a dummy index. Why is it dummy? It is dummy because you can replace j with anything. You can j with k, you can replace j with m. It is anyway summed over, right? The final result should not depend on j. The final result depends only on I. So I is a free index. That is important. I is a free index and j is a dummy index. So repeated indices are dummy indices. Once something is repeated, it means it is summed over that index. That is what is summation convention. If you have any repeated index, it means you're doing a summation over that. Therefore, the final result will not depend on that index. However, if you have an index that is not repeated, then every term, so this group is called a symbol group. This is called a symbol group. And every symbol group must have that index. Such indexes are called free index. And the final result will actually depend on that free index. So we have looked at summation convention. We have looked at symbol group. Symbol group is just a product term which has some number of indices. So, so you have free indices. A free index does not repeat. And all the symbol groups have the same free index. Same free index or same set of free indices. You cannot replace a free index with something else. Reason is, say in this case, you write bi is equal to aij xj. But you cannot write. You can replace j with k. Nothing will happen. You can put aik xk, which still means the same thing. You're summing over k. Or you can put aim xm. But you cannot replace. If you put, you cannot write this as. You cannot write this as apj xj. The reason is, on the right hand side you have a p, left hand side you have an I. There is no relationship between the two. So all the symbol groups must have the same free indices, and dummy indices are you can replace them. They are repeated indices. They are repeated only twice. No index can repeat for more than 2 times because it comes from the summation convention, right? We cannot have an index repeating more than 2 times. If you have an index repeating more than 2 times, then it's basically junk. A dummy index can be repeated twice. Free index cannot be repeated. And the summation convention is implied. That's what it means. Now we have this symbol called Kronecker delta. You would have come across it in various contexts. So delta ij is yes.
Yes, Naresh. So that dummy index can repeat more than twice, or it should repeat only twice?
It should repeat only twice. No index can repeat more than twice.
Okay.
So dummy index repeated 2 times. Free index does not repeat. That's all. There's no other kind of index that is allowed by the summation.
Okay, fine. Yes.
So you have the Kronecker delta, which is a symbol which takes the value 1 if I equal to j, and takes the value 0 if, sorry, what did I do? I not, if I equal to j, it is 1, and 0 if I is equal to j. So if you take delta 1 1 is equal to 1, delta 1 2 is equal to 0, delta 4 7 is equal to 0, delta 2 2 is equal to 1. It's like this. So if the two indices are equal, it takes a value 1. If the two indices are unequal, it's a value 0. These are just useful in further derivations, in advanced derivations in continuum mechanics. We also have another symbol called the Levi-Civita or the permutation symbol. Levi-Civita or the permutation symbol. So this, there are two cases, right? I equal to j or I not equal to j. In contrast, Levi-Civita has 3 indices. So with 1 index, it is a first order tensor. With 2 indices, it's a second order tensor. With 3 indices, it is a third order tensor. So this can take a value of 1 if I, j, k are in the order 1 2 3, 2 3 1 or 3 1 2. So this is a permutation symbol. These are all called, so you put 1 2 3 on a circle. and go in the counterclockwise permutations. So all counterclockwise permutations of 1, 2, 3 give the value of +1. Take and this value takes a value -1 if you go in the clockwise direction. So if ijk is 132, 321, or 213. In these cases, ijk takes a value of -1. And in all other cases, it takes a value of 0. So if any of the indices are any two of these indices are repeated, then it takes a value 0. So these are the permutations you can take without repeating, right? If with repeating, it takes a value 0. Now there's a beautiful identity in continuum mechanics between there's a relationship between this Kronecker delta and the Levi-Civetta symbol. That's a beautiful identity. It's useful for certain results. This is what, yeah. Let me write it down here. The epsilon delta identity. Take this as, so it says epsilon I j k epsilon I L M is equal to, yeah, so let's make a guess. So should the right hand side depend on I?
Yes.
No, right hand side should not depend on I, right? Because I is a repeated index, which means you are summing
Okay.
over I from 1 to 3. So right hand side should not depend on I. Therefore, right hand side can depend only on J, K, L, and M.
Okay.
So because when you sum over, the index just vanishes, right? It's just like, so this is basically epsilon 1 JK, epsilon 1 LM plus epsilon 2 JK, epsilon 2 LM plus epsilon 3 JK, epsilon 3 LM. So once we sum it over, the index I vanishes. So the right hand side is nothing but this identity is, so you take the like pairs, right? JL delta KM minus delta, then take the extremes and means. So it's like delta JM delta KM. The proof of this is, it's like if you just expand everything, right? If you expand epsilon IJKS with all its special cases, it's direct. We can just prove it. So this is called epsilon delta identity. It is useful for deriving certain formula for vector product of 2 or 3 vectors, the cross product and things like that. Now, interestingly, the cross product of 2 vectors can be expressed as epsilon ijk ei, which is a basis vector aj. Right now, let us prove this. Okay, so okay, so show that this is a problem. Let us prove this. So show that the cross product of 2 vectors is a cross b is given like this. You can start with anywhere. Yeah, start anywhere. So a you can write it as a1 e1 plus a2 e2 plus a3 e3, and b you can write it as b1 e1 plus b2 e2 plus b3 e3. So if you recall how we do cross products in class 12 or in the undergrad, you arrange the vectors like this, the basis vectors like this. So it can be x cap, y cap, z cap, or even e2, e3, and you arrange the components like this: a1, a2, a3, b1, b2, b3, and take the determinant of this with sign. So it is e1 times a2, b3 minus a3, b2 plus E2 times A1, sorry, A3 B1 minus A1 B3 plus E3 times A1 B2 minus A2 B1. Expand it, so you get E1 A2 B3. This is one permutation. plus minus 1 times E1, A3, B2. And again plus 1 times E2, A3, B1 plus minus 1 times E2, A1, B3 plus 1 times E3, A1, B2 plus minus 1 times E3, A2, B1. So if you look at all these terms, if you look at these indices I, j, k, these are all the positive permutations, right? It's 1, 2, 3, 2, 3, 1, 3, 1, 2. These are the negative permutations 1, 3, 2, 2, 1, 3, 3, 2, 1. And in none of these cases, all three have any of the indices are repeated, right? Everywhere it's either 1, 2, 3, 2, 3, 1, 3, 1, 2. There's nothing like 1, 1, 2, 1, 2, 2, things like that are repeated. So this you can express it as I, j, k, sum all the cases where this is plus 1, right? A, j, v, k, e, I. Right? So if you expand it, all the repeated indices cases will vanish. So this can only take 6 values. 1, 2, ijk can only take these values 1, 2, 3, 2, 3, 1, 3, 1, 2 with a plus sign. And with a minus sign, it can take these values, which are 1, 3, 2, 2, 1, 3, and 3, 2, 1. And if you expand it, it's precisely this. E1, A2, B3, which is this term. E2, E2, A3, B1, which is this term. And E3, A1, B2. And with a minus sign, it is E1, A3, B2, E2, A1, B3, and E3, A2, B1. Therefore, a cross product can be concisely represented in terms of the Levi-Civita symbol as epsilon ijk, aj, bk, ei. So this question is done. The next idea is okay. Before that, let us also look at some more properties. So what about this? Let us take two vectors, E1 dot E1. So dot product of two vectors is what? Dot product of you're taking a basis vector dot product
0.
with itself. No, dot product with itself. Right? E1 dot E1. E1 dot E1 is
Okay.
1. When 1 is
1, yes.
E1 dot E2 is 0 because they are perpendicular.
0.
So E1 dot E1 is magnitude of E1 square cos the angle. So it's when these two for the basis vectors, when EI dot EJ is what? EI dot EJ is 1 if I equal to J and 0 if I is not equal to J. But what is this? This is how we define the Kronecker delta Ij. Now, this is one thing. Now, there is something called the substitution property of Kronecker delta. Substitution property of Kronecker delta. So suppose we have an expression like delta Ij Aj. What is this equal to? So let us identify the dummy indices. These are the dummy indices. And I is a free index. So it is delta I1 A1 plus delta I2 A2 plus delta I3 A3. So what does this mean? But I has to take either the value 1 or 2 or 3. It cannot be all the 3, right? So among this, only one of them will survive. Others will be 0 because when if I is not equal to 1, this term will vanish. If I is equal to 1, these two terms will vanish. If I is equal to 2, these two terms will vanish. And if I is equal to 3, the first two terms will vanish. So depending on what the value of I is, one of these terms will survive. So if 1 is equal to I, 1 will survive. If 2 is equal to I, 2 will survive. And if 3 is equal to I, 3 will survive. So so what survives is basically AI, right? So if 1 is equal, so basically this is equal to AI. So just if you find it difficult to visualize in terms of I, put I as 3. So when this is delta 3j, A3 will survive. When delta 2j is there, A2 will survive. So when delta ij is there, AI will survive. So this is a substitution property. When you have delta ij multiplying something, aj, what survives is AI. So similarly, if delta ij is multiplying a tensor, ajk, what survives is aik. So whenever you have something, delta ij multiplying something, in place of j, substitute I. So this is the substitution property of delta. So now we'll look at the next result, scalar triple product, right, which we also call as box product. So the scalar triple product of three vectors is defined as A dot B cross C. Let us derive this. Let us see how to express it in indicial notation. Before that, let us also look at the dot product of two vectors, right? A dot B, right? What is A dot B? A dot B is in summation notation. A you can write it as AI, EI, and B you can dotted with. B you can write it as, can you guess? What should I put here?
BIEJ.
So this means it is summed over I, right? A1 E1 plus A2 E2 plus A3 E3. Similarly,
Yeah.
B is B1 E1 plus B2 E2 plus B3 E3. So what should I put here? Should I put
BJ EJ.
yes, correct. It is BJ EJ and not BI EI, because you cannot have an index repeating more than 2 times. Because this is a product, you cannot have it more than 2 times. Every product is a symbol group. So I cannot repeat more than 2 times. We have already used I twice, so I have to use something else. Now AI and BJ are just what? They are just scalars. So it is just AI BJ, and the dot product is actually here EI dot EJ. What is EI dot EJ? EI dot EJ is delta IJ. You have AI BJ. So delta has the substitution property. So in place of J, you put I. So it is just AI BI. But now I has become a dummy index, so it's also equal to AK, BK, or anything AM, BM. So dot product between two vectors is defined like this. Now that is fine. So here when we have a dot product, it's okay. Now let us write A as AI, EI dotted with cross product of these two. What is the cross product of these two? It is epsilon. Can I put IJK? Can I put IJK here? This is one term. I've already used I twice, so I cannot put IJK. Let me use PQR.
Yes. PQR.
Yeah. So by this result, right, which we just proved, A cross B is this. So B cross C is epsilon PQR, EP, BQ, and CR. So here it is EP, BQ, CR. As usual, these two are scalars. So you can just collect all the scalars together, AI, BQ, CR. And I have epsilon PQR, which is also, it's a tensor. It's a component of a third order tensor. And the dot product is only between these two, which is EI dot EP. EI dot EP is delta IP, epsilon PQR, AI, BQ, CR. What does delta IP do? Delta IP substitutes wherever P is there with the symbol I. So in place of P here, I'll put I. So it is nothing but epsilon IQR, AI, II, BQ, and CR. So an expression for the triple product is this. Now this is also consistent with the determinant form of a triple product, right? So the volume of a parallelepiped is given by A1, A2, determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. Now compare it with the cross product. In the cross product, you have EP, right? So there it was E1, E2, E3 with the determinant. So the determinant of three vectors, or this can always be written as the Levi-Civita symbol or the permutation symbol epsilon IQR, AI, BQ, CR. Now Q and R are dummy indices. I is also a dummy index. So Q I can replace with J, and R I can replace it with K. So the scalar triple product in indicial notation is epsilon. I can put ijk, ai, bj, ck. Now we have something called the vector triple product. So let us express that in terms of the indicial notation. So vector triple product is A crossed with B cross C. Now this I can write it as A cross B cross C. We have the symbol, permutation symbol, epsilon ijk ei bj ck. Bj and ck are scalars. I can take it out. So I have bj ck A cross. This is also a scalar, so I can take it as A epsilon ijk bj ck A cross ei. Now you should be careful because a cross product is not commutative. If it is, you cannot write it as ei cross e. It's always A cross E. So here you have epsilon ijk bj ck. This cross product you can write it as again epsilon. I have already used I, J, and K, so let me use some other indices. P, Q, R, EI, component of the first vector, AQ, sorry, not I, EP, I'm sorry. So this has to coincide with the index of the basis vector, EP, AQ. This is also a vector, EI, but whose rth component? So you are taking a basis vector EI, generic basis vector EI, and you're looking at its rth component. So if this is a basis, if I and R are the same, so for example, let's do it with an example, right? If you take E1, its first component is 1. So E1 is nothing but 1, 0, 0 in the same basis. So its first component is 1, but its second component is 0. So EI's jth component is equal to 1 if I equal to j, and 0 if I is not equal to j. So E1 first component is 1, second and third components are 0. Similarly, E2's second component is 1, first and last components are 0. Similarly, E3 first and second components are 0, last component is 0. So rth component of EI is 1 if I equal to R and 0 if I is not equal to R. So what it is just the Kronecker delta. So this I can write it as epsilon ijk bj ck epsilon pqr ep aq eir is delta ir. Now again, this has got the beautiful property of replacement. In place of r, you can replace I. So this becomes epsilon ijk bj ck epsilon pqi ep aq. You take the EP outside, that's the basis vector, and the rest of it is epsilon ijk, epsilon pqi, bj, ck, aq, ep. Right, this is there. Let me continue on the next page. Now you remember that the definition of the Levi-Civita symbol is such that where did I define it? Here, yeah. So it is such that for all combinations, for all positive permutations, it takes a value 1, and negative permutations, it takes a value -1. So in these indices, if I just cycle these, so epsilon, if epsilon ijk is equal to 1, it means that epsilon ijk, epsilon jki, epsilon kij, all are equal to 1. And if epsilon ijk is equal to -1, then epsilon jki, sorry, ijk, if you cycle it, ki and epsilon kij all are equal to 1, all are equal to -1, right? Therefore, if you cycle these I, j, k in the same order, this value will remain unchanged. But if you cycle it in the opposite order, right? Now, if you take it as, if you just take this as epsilon j I k, epsilon kji and epsilon ikj, these will take the value +1 because you're cycling it in the opposite direction. So you will take the other value. So you are allowed to rearrange the indices in the same cyclic order. Put this ijk on a circle and take the same order without altering the value of the resultant. Right? The expression, without changing the value of this whole expression, you can cycle the indices. So let me cycle the indices, and I can write PQI, epsilon PQI is nothing but epsilon IPQ. Therefore, I can write this expression as epsilon ijk, epsilon IPQ. What is left? BJ, CK, AQ, EP. We have BJ, CK, AQ, EP. Now note that everything is a dummy index. J is repeated, K is repeated, P is repeated, Q is repeated. What is this? This is expression for A cross B cross C. Right. Let us simplify it further. Now you see this, this has two epsilons and the first index is the same. So now use the epsilon delta identity. So when you have the first index, leave it. So if you want, you can look at it here. Yeah, you can use you can look at it here. First multiplied by first, second, minus first, second, first, right? That is how it is. So use the same format, substitute in that. So this you can write it as delta JP delta KQ minus delta JQ delta KP multiplied with BJ CK AQ EP. Now these are two different terms. This is a scalar multiplication. This will just distribute. So this becomes, sorry, this is the final point. This becomes delta JP delta KQ BJ CK AQ EP minus delta JQ delta KP BJ CK AQ EP. Use the substitution property of the Kronecker delta. So here delta will replace the P into J and it will replace the Q into K. So what do we get? Let me write it here. Otherwise it's difficult to see for you. So P will be replaced by J. So we get BJ, CK, and Q will be replaced by K. So AK and P will be replaced with J, E, J. Minus, what is the other value? Here Q will be replaced by K, P will be replaced by, Q will be replaced by J, and P will be replaced by K. Minus BJ, CK, AJ, and EK. Right? Now look at this.
Naresh, can we
Yes.
replace BJ with the BQ?
We can also do that.
After
The result
minus?
will be, yeah. We can also do
Same,
that.
no?
Same will get.
Okay. Okay.
Because the delta is symmetric in both its arguments, you can do either of it.
Okay.
So
here you get the CKAK, and here you have, yeah. So let me just write it as CKAK BJ minus, here I get BJ CKAK. What is CKAK? We just defined it, just derived it here, right? A little ahead of this. Yeah, here or here, yes. So A dot B is AI BI, or A dummy index, B dummy index, which means here CKAK is nothing but C dot A. So this I can write it as the final expression is C dot A. And what is BJEJ? BJEJ is nothing but the vector B minus BJEJ is B dot A, and CKAK is the vector C. So let us check if that is the given expression. C dot A B minus B dot A C. Yeah. Okay. I didn't. That is the correct expression, of course. So you can type this A cross B cross C as C dot A. Yeah, this is in like class 12. So it's C dot A B minus A dot B. C. I'm right. A dot B C. Yes. Yeah. So usually the rule is take the near one first and the far one. Let's multiply with the far one and multiply. So this is the expression for vector triple product in terms of the indicial notation. So what was crucial in deriving this is the epsilon delta identity. It's an application of the epsilon delta identity. We have some more questions and about 10 more minutes. But it's important. And I didn't go through tensors actually. These you can actually refer to the videos that will be more helpful. There is only one question based on tensors, skew symmetric, and this in assignment 3. Sorry, in assignment 2, there is one question based on this dyadic product of two vectors and this one based on symmetric and skew symmetric tensors. That you can do, it's not difficult. If you just refer to the videos, you'll get the answers there because those are theoretical questions. I would rather go through these problems. These are somewhat involved. So this will also help you avoid some simple mistakes. Let us maybe try proving A, B, C, and C of D because we have little time left. Any doubts so far? Any doubts?
Can you explain that in slide I think 24 or before some problems were there, no? In that first question, can we discuss that for 2 minutes?
Yeah, I missed it. Yeah, I forgot this. Yeah, I was supposed to do this. Yeah. So this is this a valid expression, right? So is this a valid expression? That is the question. So for an expression, this is an indicial notation. What are the rules? No index should be repeated
More than twice.
more than twice. Sorry, not equal to, greater than twice.
Yeah.
And a dummy index repeats twice. Free index does not repeat. And it is present in all the terms. Free index has to be present in all the terms. Now let us look at this expression. So on the left hand side, we have I and j which are not repeated. So I and j are free indices. Right? So I and j are free indices, which means on the right hand side, in all the terms, I and j should appear only once. So let us see the first term. Here I is appearing once, j is appearing once. So this is okay. This condition is okay. So in this term, free index is appearing and it is appearing exactly once. So this term is okay with respect to the free indices. And what about this term? Here I is appearing once, j is appearing once. So here also, this term also satisfies the free index. So free index is present in all the terms and it does not repeat and it appears exactly once. What are the dummy indices? So whatever does not appear on the left hand side are the dummy indices. So here K, L are there on the right hand side, but not there on the left hand side. But if it is a dummy index, it has to be repeated exactly 2 times in every term. So if you see K is repeated twice, L is repeated twice. Here also K is repeated twice, L is repeated twice. Therefore, it satisfies the condition that no index repeats more than twice. Dummy index K, L, L, each of them repeat exactly 2 times in every term on the right hand side, and it does not appear in the net result. And free index does not repeat. Yes, I and j are not repeating on the left hand side, and they are not repeating in any of the terms on the right hand side. And there is also no unknown free indices. So if I just have another plus mk, mr or something like this, r is an unknown orphan free index which does not have appear on the left hand side. This is also not allowed. So these conditions are satisfied. So this is a valid expression.
Okay.
Okay. So can we go to this? Some of these are just
problem.
yeah. So let us. The simple one is B. B is very simple, but it's slightly tricky. You have to. It's easy to make mistakes. So let me ask the steps you can. So grad operator, if you know, if you recall, grad operator is del by del x1, yeah, e1 plus dou by dou x2, e2 plus dou by dou x3, e3. This operates on some scalar. So divergence is just dot product of grad with some. So this grad operator, this is also having some repeated indices, right? X1, E1, X2, 2. So grad operator, concisely, it is represented as EI dou by dou xi of something. This can be a scalar, vector, or tensor. So this is the grad operator in indicial notation, in summation convention. Now, so we have grad operator as this thing. Grad operator is EI dou by dou xi of something. Now divergence of a vector field V. V uses a function of x is what? It is grad dot that vector field, right? So it is EI dou by dou xi. This is an operator. This is dotted with the vector field V. But the vector field also you can express in the same basis. So it is, so what should I put here? It's dotted with, how do I express V as?
Yes, VJ.
Vj and Ej, right?
Yes.
Yeah, because the direct notation does not have any indices. So you should always have dummy indices when you put it here. Right. Now, again, this is the basis vectors are independent of the coordinate system. In Cartesian coordinate system, the basis vectors are independent of x, right? So you can write this as EI dot EJ, and the operator acts only on VJ. If EJ is dependent on the x, then the operator will also act on EJ. But here in Cartesian, the basis vectors are fixed. The coordinate system is fixed and only the components are varying. So this will only act on Vj. So we have dou by dou xi Vj. What is this? EI dot EJ.
E dot.
Yeah, so EI is one basis vector. EJ can be another basis vector or the same basis vector. So EI dot EJ will be delta ij, right? If I is equal to j, yeah. So it is delta ij partial Vj partial xi. Now this has the substitution property, so I can write this as
again I dou Vi by
dou xi.
yes.
Don't replace both, right? We have to replace only one of the indices that you have to take.
Okay.
Like if you put I here and j here, it makes no difference, right? So you have to replace only one of the indices.
Okay.
Fine. So the gradient of a vector field, sorry, the divergence of a vector field V is nothing but partial Vi partial xi. Fine. Now what is the given vector field? It is just x. We are just given x, right? So in place of V, just put x. So the divergence of x, the position vector is partial xi, partial xi. What is this equal to?
It is 1, no?
No, that is the problem. So we are so used to looking at things, right? So dou x1 by dou x1 is equal to 1. Dou x2 with respect to dou, so x1, so if you have a function f of x1, x2, x3, and if that function does not depend on x2, dou f by dou x2 is equal to 0. But x1, x2, x3 are independent, so dou x2 by dou x1 is equal to 0. Dou x3 by dou x1 is equal to 0. But here you have a repeated index, right? I and I is not fixed. So if you have dou x1 by dou x1, it is 1. But I is not fixed. So this means summation convention. So this is equal to dou x1 by dou x1 plus dou x2 by dou x2 plus dou x3 by dou x3. So in Einstein's notation, there is a summation here over I going from 1 to 3. So this is 1, this is 1, this is 1. So the answer is 3. So that's a common mistake people do. Even I have done this mistake some point in my coursework. So you get this. The divergence of x is 3.
Yes.
Similarly, yeah, all of these can be straightforwardly proven. If you just express this in indicial notation, express this in indicial, it will directly fall into this. Just as we proved for this triple product, the steps might be longer, but at every step, make sure for the delta, use the substitution property. And when you get terms like UK, WK, write it as U dot W. And yeah, and when you have this cross product, use the epsilon BQ. So maybe in 2 minutes I can do this. This is probably shorter.
Yeah, okay,
So,
no problem for me.
Okay. Okay. So fine, if you can try this out, and we can also discuss the answers in the next session. I'll post the thing. The link is now available in the course webpage. So both the recordings and the presentation I'll post in there. Okay, thanks for attending. If you have any doubts, you can ask. We stop recording.
Okay. So actually that question, third question is there, no?
Yeah.
So in that, how to solve for that phi? Phi of u is there, no?
We are not solving for phi. We just have to show left-hand side is equal to right-hand side.
Okay.
So it's like, it's just, so we have del cross, curl of phi u, right? U is a vector field, phi is a scalar field. We have to show the right-hand side comes from that. So you just use the indicial notation. So grad is what? Grad is EI partial with respect to I. This is grad operator cross producted with no, we don't need to do the grad operator. So grad operator, you know, so grad operator is EI dou by dou xi in Cartesian coordinates. But this cross product, you can write it as epsilon ijk. What is the component? So first vector is this. Grad is the first vector. Its jth component is what? It is dou by dou xj, right? So ith component is dou by dou xi. So let me write. So it is this plus grad operators jth component and phi use kth component, right? This you can agree. So this is a cross product of two vector-like objects. So you put the Levi-Civita symbol. The first vector-like object is the grad's jth component, and phi use kth component. Now, what is EI is fine. What is grad's jth component? So this is just dou by dou x1 E1 plus dou by dou x2 E2 plus E3 dou by dou x3, right? So kth component has dou by dou xk. So this jth component is nothing but dou by dou xj acting on this thing. So U is a vector field. So U is something like U1, E1 plus U2, E2 plus U3, E3. But phi is a scalar field. So phi is just a number which gets multiplied with all the components. Right? So kth component of U is what? It is just, so third component of phi U is phi U3. Second component is phi U2. First component is phi U1. So kth component is phi UK. Now just apply the product rule here. So we have epsilon ijk ei. Use the product rule. You get partial phi with respect to xj uk plus phi uk xj. Now multiply the Levi-Civita inside. You get epsilon ijk ei dou phi by dou xj uk plus epsilon ijk ei phi dou by dou xj acting on uk. Now by inspection, what is this? This is epsilon ijk ei jth component of grad phi, right? So second component of grad of a scalar is dou phi by. So if you just put a phi here, you get a phi everywhere. So second component is dou phi by dou x2. So third component is dou phi by dou x3. So dou phi by dou xj is jth component of grad phi. So this is nothing but epsilon ijk ei grad phi's jth component uk plus epsilon ijk ei. Phi is a scalar and it doesn't have any indices. You can take the phi out. And this is dou by dou xj is jth component of grad operating on kth component of u. So this is nothing but phi curl of, so this is like grad cross u. So this is curl of u. And here what do we have? Here we have a, so this is jth component of phi and the kth component of u. And this is epsilon ijk. So this is grad phi by cross product definition. This is grad phi cross. So this is what we needed to prove. Del cross phi u is this. Grad phi cross u plus phi acting on phi times curl of u. So this is what we have here. Yeah, grad phi cross u plus phi del cross. So if you just do it systematically, they are all straightforward. But it's very likely to make mistakes. Once you avoid it, you do. Okay, right?
Yeah, okay.
Okay, if you have any doubts, you can post in the group in that discussion forum, or you can also write to me.
Okay, okay. Okay.
So I'll end the session.
Last two problems and I will let you know.
Okay.
Yes.
Okay, thanks for attending. I'll end the session here.
Okay, okay, yeah, bye. Yeah, thank you.